Hello, welcome to the class of antenna and web propagation. So we are discussing the basic parameters of the antenna, and we have discussed the radiation density or radiation power density. That is the radiation at any point in a given direction. Radiation at any point in a given direction. Now we will discuss what is radiation power intensity. What is radiation power intensity? So the second term, the radiation power intensity. So radiation power intensity. This is very important antenna parameters. See, the previous we have discussed. Suppose this is antenna, wire antenna, and this wire antenna is radiating in such a manner that in this direction, in this direction, in this direction, in the downward, this, this, this. So this wire antenna is radiating in the given direction. So in the previous, the radiation power density will give you the power at any point in a given direction. But in the radiation intensity, this will give you power in any direction from the antenna, in any direction. ये किस डायरेक्शन में कितना पावर दे रहा है ये बताएगा। और पिछला जो डेंसिटी था किसी एक पर्टिकुलर डायरेक्शन में किसी एक पॉइंट पे कितना पावर है वो उसको इवैल्यूएट करने के लिए यूज करते थे। तो प्रीवियसली हम यहाँ पे जो पावर डेंसिटी दिखाते थे, रेडिएशन पावर डेंसिटी, सो दिस पावर से रेडिएटेड पावर W upon the incremental area for the power density. Okay. Here we have to understand the concept of the solid angle to estimate the radiation in a given direction. So first, let us understand what is an arc, how this distance of the arc vary with respect to the angle and the radius of the any area or figure. So suppose this is your arc. So this arc has an angle, say theta, and this is the radius r of this given arc. So now here this length is proportional to this theta. If theta got wider, suppose this theta is shifted from this, then this length will get increases. So it is obvious from the figure that this L is proportional to the theta. Now, what about the radius? Whether it is proportional to the radius or not. So, if we increase this radius, say this is radius, length r. So this is angle theta. Now here length is L. Now we further increase the radius. For a given, keeping this angle constant. So this will be the length, new length. So see, this L is also proportional to the R. As the radius increases from this point to this length also increases. Okay? So this shows that this L is a function of theta and R. Okay? So this L is a function of theta and R. Now if this theta, if we multiply this radius with 6.28, then this length will become complete circle. Complete circle. That is this, which is also called 2 pi. So the complete circle, the circumference of the circle. So this L is equal to the circumference. Of the circle. So here, this wide opening of theta will result in increase in the length, and we cover this entire circular area, 2D area. You have to multiply this radius with, that is, the angle should be 6.28 or 2 pi. You get a complete circle. So in similar manner, when antenna radiates in a given direction, so this is the antenna. Suppose it radiates in any direction. So this radiation is not only dependent on the theta, but also the angle. That is the angle opening horizontally and angle opening in the vertical manner. Horizontal manner and the vertical manner. Both. So a complete cone, like a conical shape. A complete conical shape. But not this having a flat surface, but the surface is like this. So this shape, the opening is here, is called the solid angle. And it is ds. So this is a solid angle. Solid angle. Okay. So here, this is proportional to R, and this is solid angle. If we have this ds surface, then ds is equal to this solid angle and the R square. So surface, total surface, S equal to sigma R square. So ds is d sigma R square. Yes, one angle, that is angle, is proportional to R, and another angle proportional to R into R square, solid angle. So 2 dimension to 3 dimension, complete angle. So it will extend a surface area ds, cover a surface area ds. So instead of it to be length L, it will become a surface, and this surface is obviously proportional to this R square of the radius. This is the radius R. So this ds has a relationship with dl, solid angle as R square. So from here, this ds by d solid angle is equal to R square. This is very important relationship of the surface in the solid angle. Very important relationship of the surface with the solid angle. So now suppose one thing more. Here to complete entire surface area, that is in the entire radiation pattern. Instead of 2 pi, here you have to multiply this s is equal to 12 point something r square. Okay. So 12.56 near, or we can say this is 4 pi r square. That is the complete spherical surface. So this solid angle covers the complete spherical surface. Now, correlating it, the unit for the power density is watt per meter square. Now, for solid angle or radiation power density, this is power intensity. If this theta for a 2-dimension has a unit of radians, then this solid angle, which is in 3-dimension, has a unit of steradians. Steradians. Okay. So steradians. So this is power intensity here. Can be given by dW upon the solid angle, and it is in watt per stereo. So power oblique direction or power oblique. So power in a given direction, so power by direction. Power by directions or power by solid angle is. Okay. So this is the relationship. Now we have this found as or isotropic radiators or for a spherical shape, the surface area ds for spherical shape or coordinate the surface area ds can be written as r squared sine theta d theta d phi. So ds is equal to r squared sine theta d theta d phi. And we have a relationship that ds is equal to d sigma into r square. So ds is equal to d sigma into r square. So from here, this ds is equal to d sigma into r square. So from here, this solid angle can be, this is 1, this is 2. So from 1 and 2, this d sigma is equal to sine theta d theta d phi. Okay. So this is sine theta d theta d phi. So this r square term is not there in this. R square term is not there in this radiation intensity. Okay. So power density, if we have seen that it has a component of the power in the direction of, that is taking ds. So it has r, theta and phi. So r, theta and phi. It has the components of in all the three coordinates of this paper. That is, it has a dimensions, magnitude, as well as depend on the angle. Both depend on the magnitude and the angle. Okay. Now, in the sigma, the r square term is not there. So it is only dependent on the. So it is only dependent on the angle or direction. Or this can be denoted by u to differentiate it from the power density. Okay, so it is denoted by u to differentiate it from the power density. Now to evaluate the power intensity, so d omega upon r upon solid angle. This can also be written as d omega r upon ds into ds upon d solid angle, and this is equal to this. If this is equal to 1 upon 2 e t square r comma theta comma phi by the intrinsic impedance of free space eta, then this can be written as 1 by 2 e square r theta phi, and this ratio ds by is called r square. So here, this r square term is here and it has no magnitude. So this no magnitude. So this can be written as this. That is u theta comma phi into r square. Okay. So u theta comma phi, or sorry, this complete is p r comma theta comma phi, and this is u theta comma phi. Okay. Now, we extend our analysis for isotropic case, for isotropic radiation case. Let us say for isotropic antennas. for isotropic antenna. So power density, that is d omega upon d s. So isotropic antenna radiates equally in the all direction, that is the total surface area of the given sphere. Equally in the all direction, that is total surface area of the sphere. So this will be divided by the power radiated, total power radiated upon 4 pi r square. So this differential becomes simply a division. So this differentiation simply becomes a division. Okay? So that is it. This is P in the magnitude r comma theta comma phi. And this is also an average power. Average power, that is direction dependent. Direction dependent power radiation. Okay. So direction dependent power radiation. Now, what happens for the power radiation in all direction uniformly? So, power direction in all direction uniformly for isotropic case. So, we have this d omega r upon d solid angle. So, this solid angle is, instead of u, it does not have any magnitude but have direction. So this will only divided with, it does not have any magnitude but have only direction. So omega r upon 4 pi. As from the relation ds by d sigma is equal to r square. Okay. So ds and ds by d sigma, it will give you omega r upon 4 pi and r square is cancelled out. So this can be written as u average instead of here u average, that is radiated power, radiation power intensity. So this is a radiation power intensity. So this is a very critical concept related to the radiation power intensity and radiation power density. And this is very important antenna parameters. And in the examination, lots of numerical problems are based on these questions. Okay. So now we'll see the another parameter, important parameter of the antenna, that is the gain of the antenna. The gain of the antenna. What is gain? Gain of the antenna. So gain of the antenna. So gain of the antenna are generally three types. They are generally of three types. So they are generally of three types, and we will see all these types one by one. Okay. So the power gain, these types are the power gain. First, the power gain, we categorize how gain of the power is achieved for the given antenna, and then directive gain, that is the gain in a given direction, and directivity, the maximum gain. So power gain, power gain. So this can be written as G, capital G, G denoted by power. Then directive gain, okay. Then this denoted by capital G to B, and then the directive. Directive. So all these three important parameters are come under the category of the gain of the antenna. So we will see these three types of gain one by one. So first, starting with the directive gain. So this directive gain is the radiation intensity of the given antenna with respect to the isotropic antenna. The radiation intensity of the given antenna with respect to the isotropic antenna is called directive gain. The radiation intensity of the given antenna with respect to the isotropic antenna is directive gain. So, taking second one first, the radiation intensity of a given antenna the radiation intensity of the given antenna with respect to the with respect to the isotropic antenna for directive wave so directive wave. Mathematically, we can write it as this can be written as mathematically this radiation intensity of antenna upon radiation intensity of isotropic antenna. So GD So isotropic antenna. So this ratio is called directive gain. So it can be denoted by radiation intensity, and we have seen that this intensity is given by denoted by u theta comma phi. That is, there is no r term, magnitude term. It has only direction terms. So this upon this, that is the average power of the isotropic antenna. So P average. Okay. So this antenna U radiation comma phi and P average, that is power density of the isotropic antenna, is PR upon 4 pi r square. Sorry, this is the intensity term, so 4 pi r, 4 pi. Okay. Radiation intensity, so 4 pi. So this can be written as 4 pi u theta comma upon the radiated power. So this is directive gain. In the mathematical form, this is the directive gain. Okay. Now, what is power gain? Power gain. In the power gain, the formula is simple, and the power gain, the formula is similar to that. This, but here you have to take one more term to define it in the form of the efficiency. That is, so power gain. Simply power gain is the total power radiated upon the input power. Total power radiated upon the input power. Okay. So this can be written as so this power in GP, that is the first term, GP can be written as this u theta comma phi upon this u theta comma phi upon the input power, that is V upon 4 pi, and this will become 4 pi into u theta comma phi upon V input power. If we write it in the W form, P or W, you can use any notation. So multiplying and dividing it with the W, it will give 4 pi u theta comma phi upon W r into this W r upon W. So this term is the directive gain and this is the efficiency. So this power gain can be correlated with the directive gain with respect to the multiplication of the efficiency with respect to directive gain will give you the power gain. Okay. So here efficiency is WR upon W input. efficiency can also be written as WR on WN, that is WR, and this input is combination with the radiated power with the losses. So these are the losses are only this power is radiated and this power is dissipated in the form of loss. So this is the complete input power. And in terms of radiation resistance, this RR is equal to RR plus RL. So this is the complete efficiency. Okay. So this is the directive gain and directive power. Directive gain and directive power. Now, directivity, what is directivity? So, directivity, which is denoted by capital D, is equal to KD max. That is the maximum value of this directive gain. The maximum value of the directive gain. And its value is always greater than or equal to 1. Always. Because if we have a situation of this isotropic antenna, so this isotropic antenna radiates equally in all the direction. That is, this is the ideal case. So if we take power, that is power is equal or in all the directions. So if we take average power, so average power divided by the power, that is power is equal in all the directions. So it will definitely give you 1. Now for practical case, this is the maximum and this is the minimum. So it radiating in this direction, the radiation in this direction is very high compared to this. So this will always lead you that greater than or equal to 1. Okay. So this is the gain of the antenna. Now in the next class we will discuss other parameters of the antenna. Some other parameters of the antenna, that is the beam width and half power beam width, etc. So thank you for today. Okay.